Welcome all to this first of this Colloquium series. We are planning for this recent advances in astronomy and space sciences. I'm delighted to have Professor Jack Burns from University of Colorado as the inaugural speaker, and he's going to deliver his colloquium on radio astronomy from the moon. Just before Jack starts, I just want to introduce him to the young people in the crowd. Professor Jack Burns is professor in Department of Astrophysical and Planetary Sciences at University of Colorado, Boulder. He's the Vice President Emeritus of Academic Affairs and Research at CU System. He received his PhD degree in astrophysics from University of Massachusetts, and then later awarded MS and PhD in astronomy from Indiana University. He went on to do his postdoctoral fellowship from National Radio Astronomy Observatory, and then has an illustrious career in several universities in New Mexico. He was an associate dean for the College of Arts and Science at New Mexico State University, where he helped to oversee a budget of about $65 million and recruit a health department. He was a department head and professor in that same department later on. He was also associated with University of New Mexico in Albuquerque. Currently, he is the director of Network of Exploration and Space Science, which is funded by NASA Solar System Exploration Research Virtual Institute. Jack has over 479 publications in NASA ADS. He has published in a variety of journals, starting from Scientific American, Nature, and Science. He has been a member of NASA Advisory Council, serving as a chair of Science Committee. He has served as Senior Vice President of American Astronomical Society, the leading professional astrophysics association in the world. He's a current member of the Board of Directors of Space Science Institute in Boulder, and various other renowned councils and committees related to astronomy, astrophysics, and sciences. So it's my greatest pleasure, and I know Jack because he has been my postdoctoral mentor for a period of 5 years in Boulder, and we have lovely memories of working on this radio astronomy from the moon aspect. So with all this, I think I introduce Jack, Professor Jack Burns, and the floor is yours. Jack.
Thank you, Abhi. Can you hear me okay?
Yes, we do.
Sound coming through? Very good. Thank you. Well, it's a pleasure to be with you. Thank you very much, Abhi, for this invitation to present the colloquium today. I'm very much looking forward to it. I first want to make sure that I acknowledge a large number of collaborators, students, postdocs who are working with me on this project, particularly for two missions that I'll be talking about, mission concepts, Dapper and FARSIDE, and I'll be mentioning some specific names along the way. I also want to acknowledge funding from my NESS Center, NASA-funded center that Abhi mentioned, our Network for Exploration in Space Science. So what I want to do today is to present a roadmap, an exciting roadmap, I think, for radio astronomy from the moon at low frequencies. So what I'm going to do is I'm going to talk about two missions which are scheduled to launch in the next few years using some small landers, commercial landers. One will launch next year and bring the first U.S. instruments to the moon. This will follow on the successful Chinese Chang'e 4 landing on the far side, which had a radio science instrument, and also their communication satellite and Earth-Moon L2 Lagrange point also had a radio astronomy. So we'll follow up on that, and then I'm going to talk about a cosmology satellite called Dapper that we propose to put in orbit of the moon, and then finally this array of radio telescopes that you see pictorially on this first slide called FARSIDE, 128 antennas, which will be used mainly for exoplanet research. So let me just start right off with the recognition that that radio astronomy from the moon is not a new idea. It's something that people have been kicking around well before the Apollo 11 landing on the moon. In fact, I've got a kind of fun clip to play for you right now. This is from the famous science fiction writer Arthur C. Clarke in 1963 on British television, and he's talking about telescopes on the moon. So let me just play you a little bit of that. And I'm going to advance it here to the spot that is most relevant.
Laboratory. Now, have you got anything new to add to what you said then?
Not in principle, but I think the moon is going to be of tremendous importance as a base for scientific observations of many types. Because on the moon we have peculiar conditions which we'll exploit, as we have always on this Earth exploited novel surroundings. You have no gravity, we have low gravity, and we have atoms. This is going to be of tremendous importance to the astronomer in particular. Here on this Earth, the optical astronomer has always been severely handicapped by the fog and murk of the atmosphere through which he appears at the heavens. Even the radio astronomer is also limited on the Earth, because here there's mounting interference from electronic devices of all kinds. Moreover, he cannot build the really giant radio telescopes he would like to have, because Earth's gravity makes it an engineering impossibility. But on the moon, and particularly on the far side of the moon, shielded from the electronic racket of the Earth by 2,000 miles of rock, there's an ideal site for radio astronomy telescopes. And I think that in a few generations, almost all serious astronomy will be conducted either on the moon or in space.
Well, let's turn now, shall we, to yet another
So,
of the pioneer ideas.
this radio muck that was discussed by Arthur C. Clarke is illustrated here. The radio frequency environment on the surface of the Earth, particularly at frequencies below 50 megahertz or so, is very messy. This is LOFAR observations from Europe. This is the signal power versus frequency that you're looking at here. And you see all of this interference that is present, particularly as one goes to these lower frequencies. This is coming from powerful transmitters at a variety of different locations, digital, television. So when you also then couple that with the ionosphere, as you go below 50 megahertz, then once again, you start having issues of transparency. The plasma frequency, the ionosphere cutoff frequency in the Earth is about 10 megahertz. But even above that, you have issues of refraction and re-emission that are important issues. So just going into space doesn't allow you to escape the radio frequency interference. And that's illustrated here at the bottom left. This is data from NASA's WinWave satellite from a few years ago when it was above the moon's near side. So it was in the vicinity of the near side. This is a waterfall plot of frequency versus time. And you see all these horizontal stripes going across. Once again, that's terrestrial transmitters. At the distance of the moon on the near side, the brightness temperature of the Earth from radio frequency interference is 750,000 Kelvin. Okay, and so to put that into perspective, the kind of cosmological signals that we're going after for a redshifted 21 centimeter is in the tens to hundreds of millikelvin. So you can see that environment there. Is pretty nasty. So when you do go to the far side, as was done with NASA's RAE-2 satellite in 1972, this is a plot of antenna temperature versus time. And you can see in the vicinity above the near side how noisy it is once again. But when you get to the far side, the emission sinks down. You can easily discern the galaxy, which is going to be the foreground for much of the observations I'll be talking about today. So clearly, that's an issue. So part of the reason that the very low frequency radio astronomy has not been possible up until now on the surface of the Earth is because of the RFI and the interference. The other thing has also been just accessibility to the moon over the last 50 years or so. And then finally, up until recently, there's really been a lack of what you might call a killer application or compelling astrophysics that uniquely requires low frequency observations from the lunar far side to justify such a mission. That's changed dramatically in the last few years. Two very exciting cases have emerged. One for the dark ages and cosmic dawn, illustrated in the upper left here in this simulation, numerical simulation of neutral hydrogen, and the opportunity to be able to probe this unobserved part of the early universe. And the other exciting case that I'll talk about today with an experiment on the far side of the far side array is the magnetospheres in space weather associated with habitable planets and habitability. So those are the science cases that I want to talk about. So let me just mention in terms of accessibility, the moon, this is also dramatically changing. A number of international expeditions to the moon, including missions from India, from China, from Japan, US, from ESA. But as far as the US program is concerned, a very ambitious program is underway now to return humans to the moon called Project Artemis. For those of you who know a little Greek mythology, Artemis was the twin sister of Apollo, and she is the goddess of the moon. So the plan that NASA has is to return, is to bring the first woman and next man to the surface of the moon by 2024. Very ambitious timetable. And so in this plot from NASA, what you see is a couple of important things. One is here on the surface, you see something called the Commercial Lunar Payload Services. These are unmanned landers that are being contracted for by NASA to bring science payloads to the moon. This is a very different kind of process than what NASA has done previously, in which it is buying services from these commercial companies to bring our payloads to the moon. And the first two instruments I'm going to tell you about are going to be brought by these CLPS, that is the Commercial Lunar Payload Services program. In addition, you see up top here is the development of the Orion spacecraft, which will carry astronauts and along with that, the launch vehicle, the Space Launch System. The first flight, now called Artemis 1 of Orion, is scheduled for late next year. That will not have a crew. That'll be followed a year or two later by the first crewed mission to orbit the moon, and then finally Artemis 3 in later in 2024. At the same time, NASA, in collaboration with ESA, is building out the Lunar Gateway, which is a station in orbit of the moon. So accessibility now becomes much more viable. We've got commercial, we've got international partners, we've got NASA all going to the moon in the next few years. So the ability to bring instruments there has improved dramatically in only a few years' time. So let me tell you a little bit then about the first two missions that are scheduled to go. And both of these missions are landers, and they contain simple radio science experiments with the idea of providing a proof of concept that good, clean radio measurements can be made from the surface of the moon. And the plan is to determine whether or not the kind of high fidelity spectra that will be required for future observations, particularly from the far side, are going to be possible. ROLSES is the first mission, radio wave observations at the lunar surface of the photoelectric sheath. That's a mouthful. And this project is being led by Robert McDowell, who's also my deputy for NES, and I'm a co-investigator for this project. It's going to be delivered to the moon by a commercial lander from a company in Houston called Intuitive Machines, and the name of their lander is the Nova C. There'll be two sets of dipole antennas, one here at about 3 meters and another one coming out of the plane that's about 1 meter from the surface. These are stacer antennas. And once again, what we'll do is we're going to use the plasma density. We're going to measure the plasma density through radio emission to measure for the first time the kind of localized ionosphere that is near the surface of the moon. A lot of different models, a lot of uncertainty associated with that. We'll also look at the RFI environment, because this lander is going to be on the near side of the moon. So we want to measure that, see if there are any gaps for future observations. This will be followed a few years later by a mission called LuSEE, the Lunar Surface Electromagnetic Experiment. And this is led by my colleague, Stuart Bale at the University of California in Berkeley, who's part of our DAPPER program. Once again, I'm a co-investigator on this mission. In contrast to ROLSES, this lander is scheduled to go on the far side of the moon. This will go in the Schrodinger impact basin, which is part of the South Pole Aitken Basin on the far side, large impact crater. So 3 antennas, stacer antennas that you see here in the illustration. It'll measure electric and magnetic fields. Once again, looking at the radio frequency environment, this time on the far side of the moon, and also probe for type 2 and type 3 radio bursts coming from coronal mass ejections, which should be prominent at that time around 2024, because that's near the peak of the solar cycle. All right, with that said, so these 2 precursor missions, these pathfinder missions, are going to set the stage for what we plan as a dedicated cosmology satellite called DAPPER, which you see illustrated here. DAPPER stands for the Dark Ages Polar Emitter Pathfinder. DAPPER was selected from a NASA competition for astrophysics small satellites a couple of years ago. We were selected to do a mission concept study, and we're further funded now for an additional 2 years to develop the instrument up to a higher technology readiness level for consideration for flight. My co-investigators, Stuart Bale and Rich Bradley, are the leads. This small satellite, which has a volume less than a cubic meter, will be placed in low lunar orbit and take data only when it's above the radio quiet far side, and will operate at frequencies starting around 20, 18-ish megahertz, extending in 2 bands up to about 100 megahertz altogether. And this is just the more members of the team. We have 4 institutions. My home institution is the lead, University of Colorado. The NASA Ames Research Center is our management organization, the National Radio Astronomy Observatory, and then finally, University of California at Berkeley are the partners on this. Let me tell you a little bit about the science, okay? What is the science driver? So let me focus on the left-hand side of this graphic that you see here. It's a cartoon picture of the evolution of the universe, beginning with the Big Bang at the top, today's universe down at the bottom. And we know that the universe first becomes transparent at about 400,000 years after the Big Bang. This is when the universe is expanded, cooled, so that the first electrons and protons combine to produce neutral hydrogen. It also allows the optical depth to decrease so that we get our first picture of the universe from the cosmic microwave background. But also at this point, the baryon content of the universe is dominated by neutral hydrogen in the intergalactic medium, but there are no stars, no galaxies, so there's no additional radiation sources. This is why we've called this the Dark Ages. But there's a lot going on. There's a lot of physics going on here. You have the cores of stars are collapsing during this time period. And so the first signs of large-scale structure are beginning to form. About a half a billion years later, the first stars, according to models, turn on. They're thought to be very massive, 100 solar masses or so. They emit a lot of Lyman alpha emission, which begins to reionize the intergalactic medium. That reionization continues for about a billion years, redshift roughly in the vicinity of 6 to 8. When you have the last phase transition of the universe is completed, going from what was an all-neutral intergalactic medium to what we see today, which is an all-ionized intergalactic medium. Now, this makes for a very nice story, makes sense, but there's absolutely no data here to back it up. We have data from the CMB up here, and we have data from Hubble, which pokes into reionization here, up to maybe a redshift of 8 to 10-ish or so, but the vast majority of this time period has not been sampled. And it's not going to be easy to do traditionally because the sources, namely for stars, galaxies, are still so very weak that even the James Webb Space Telescope is not going to be able to pick them up. But there is a way to sample this because I mentioned several times about the ubiquity of neutral hydrogen at this time period. So we can use the hyperfine line of neutral hydrogen, the spin flip transition that produces the laboratory wavelength of 21 centimeters, which because of the expansion of the universe, that wavelength is stretched to meters, even kilometers, and to frequencies below 100 megahertz. And even a modest-sized telescope, because of the abundance of neutral hydrogen, is in principle able to detect a global signal. On the right-hand side, just a reminder to us how important cosmology has been to physics and astronomy over the last decade and a half. 3 Nobel Prizes associated with either ends of the observing spectrum here with CMB and also with the observations from the Hubble Space Telescope. So these early epochs of the universe are clearly important. So with DAPPER, what we plan to do is to probe the 21 centimeter global signal. Like the CMB, the neutral hydrogen also fills the sky with a signal coming from the neutral hydrogen. And it's that global signal that we will attempt to see with the DAPPER satellite. Down in the lower right gives you an example of the spectrum that we see. I mean, we'll have really with just the dipole antennas effectively no spatial resolution, but we'll have very good spectral resolution. This is brightness temperature measured against the CMB versus frequency. Because this is also a 21 centimeter line, which is different than the CMB, we also are probing redshift here. So as we go from high frequency down to low frequency, we also go from low redshift to high redshift. So sweeping through this spectrum is also sweeping through the evolution of the dark ages and cosmic dawn. So as you can see here, there are a couple of troughs that are expected in the global signal, and they're associated with fundamental physics in the early universe. So first is a dark ages trough that you see here, and these dark ages troughs that you're looking at for the standard model, which is the dashed curve here. That standard model is standard lambda CDM cosmology plus star formation, which is present over here. That dark ages trough is pure cosmology. There's no astrophysics because there's no stars, no galaxies. So in the simplest lambda CDM cosmology model, this is just what we're doing is looking at adiabatic cooling of the neutral hydrogen measured against the warmer CMB, and that produces a hydrogen trough that is expected here. And it makes a very specific prediction about what the magnitude of the trough is, that is the depth of that trough in millikelvin and the frequency. Any deviation from that is going to be a sign of additional physics, which is going to be exciting to probe. Then as you go over here, a second trough appears. This is called the cosmic dawn trough. And the turnover occurs here when the first stars turn on. I mentioned before the Lyman alpha from those stars. that couples with a hyperfine line of neutral hydrogen through something called the Voigt-Hausen field effect, which has been known for some time, and that produces this deeper trough that you see here. So measuring where that turnover occurs is actually going to tell us for the first time when those first stars form, and then the nature of the trough is also going to help us to identify characteristics of those population-free stars. Now, what you see here as well is overlaid onto the standard model are in gray is a result published by the EDGES group led by Judd Bowman. This was published now 2 years ago in Nature, a claimed detection of a surprisingly deep trough that's about 3 times deeper than what we expect from the standard model. This really was a surprise because we thought there was a firm limit on the depth that was given really by just adiabatic cooling. So this suggests, for example, among the models that have been identified, that added cooling of the neutral hydrogen is going to be necessary. This is baffling because there are not many ways that you can cool. So there's been several hundred papers now published with the idea of non-gravitational interaction between dark matter and neutral hydrogen, such that energy is transferred from the hydrogen to the dark matter. If true, that would be very exciting in new physics. And it's something that, that we would like to probe and confirm with DAPPER. All right, so the idea with DAPPER then is what we'd like to do is to address this really fundamental question that you see at the top here. Will the observed behavior of redshifted neutral hydrogen redefine the standard cosmological model, that is to identify new additional physics, maybe having to do with dark matter, maybe having to do with other sources of heating and cooling that have been speculated about. So our goal is to measure both of these troughs to reconfirm or not the cosmic dawn trough and also the dark ages. Now you see the color curves that are listed here are parametric cooling models that we've developed, and you can see they're all consistent with the EDGES result here. Very hard to break apart because this is a challenging time period, because here you do have star formations going on, black holes forming as well, and heating the intergalactic medium. In these simpler dark ages, this is really a playground for cosmology. So any added physics is much more obvious and these curves break apart. Now, one last point over here in the right shows that this is not an easy experiment. Even when you get away from the ionosphere of the Earth, even when you get away from the RFI, the challenge is that you're still trying to observe this weak signal against a strong galactic foreground. This is brightness temperature versus frequency. Here is the galactic foreground. The nice thing about that is intrinsically the spectrum is simple. It's a power law. It's synchrotron radiation. And then contrast that to the foreground. So in our approach to extracting the 21 centimeter signal from the foreground, we'll use 3 things. One is the difference in spectral shapes between the foreground and the signal. Secondly, the difference in spatial structure. At these scales that we're looking at with our large beam, the 21 centimeter signal is isotropic on the sky. And then finally, also that the foreground is going to have induced polarization by using a dipole as we rotate across that. That structure is going to induce polarization signal in Stokes Q and U. But because there's no structure in the foreground, the signal is not polarized. So we're going to use those differences to help us extract it. All right, a little bit of close-up on the DAPPER spacecraft you see located over here. We've got 2 antennas, a high-band antenna, which is we're going to be using something novel that hasn't been used before for 21 centimeter, a patch antenna. Patch antennas have been used extensively for space communication, so there's a lot of heritage. But we've also found in our modeling that they have very good characteristics. Here's a look at the beam at 75 megahertz, very clean beam here. The chromaticity is, that is the change in the beam with frequency, is smooth. Good front to back ratio that we're looking at over here. So that's going to be used for observations between roughly 60 and 100 megahertz. The low band antennas are simple wire dipole antennas, have been used extensively in space, will measure between 20 and 40 megahertz. So here is our latest modeling of what we expect to be able to see. This is a kind of end-to-end modeling. That is, when we put everything together in here, in which we include statistical errors, systematic uncertainties from the foreground, from the instrument, from the beam. This is the extracted signal that we expect to be able to get. In color, you see 68 and 95% uncertainties. And you barely notice in here, but there's also a little blue in here. Our high frequency band, because of the excellent packet antenna, has very, very good confidence. And here, plotted once again in the dashed, is the standard cosmological signal. This signal down here is one with added cooling. So we're able to, with about 2 years mission lifetime, we're able to differentiate fairly well, very well, between an added cooling model and the standard CDM model. So that's our goal. The instrumentation, we have a lot of heritage. Our wire antenna has been used on the Parker Solar Probe, Themis, Van Allen probes. We're going to also make use of the receiver electronics, particularly digital electronics, that's currently on the Parker Solar Probe. We've also been, the core receiver is a correlation receiver that will help us to reduce both onboard and external noise. That receiver has been developed for two purposes, for Dapper, but also for a new 310 megahertz system that is on the Green Bank telescope, that is going up on the Green Bank telescope by NRAO. So that's going to be tested out in the next few months as well. So that's moving forward. We also, my former student Bang Nan, who's shown here, and he's now a Jansky Fellow at NRAO, for his dissertation, built what we call the cosmic twilight polarimeter. This allowed us to test out measuring the polarimetry signal from the foreground using this dynamic polarimetry, that is to let the sky, in this case, sweep across the instrument and rotate relative to the antenna, and to detect that expected signal at the level that we expected, that is to see the variations in Q and U due to the structure in the foreground. So that worked out well. We have a next generation of this polarimeter that also is going to be placed in Green Bank soon. The last thing I want to mention with regard to this is our software pipeline that my group is focused on in Boulder here. It's a very important part of the experiment, because we can't do what is traditional in radio astronomy for this experiment, and that is simply make an observation, subtract out a model foreground, and look at the results. Because the required dynamic range and the required accuracy of knowledge of the beam-weighted foreground is simply too high. So what one needs to do is to use more sophisticated tools to simultaneously fit the foreground, the beam, the systematics of the instruments together, using techniques that involve machine learning, that use training sets and pattern recognition. We've published a series of papers, 3 in the sequence in the last 2 years, and those papers are listed here, that lay out the pipeline. The idea is the observation strategy uses the time dependence of the instrument. That is, with Dapper, we rotate across the sky so that there's change in structure, which we take into account, and also polarization. Those come together to help us differentiate the foreground which changes in those variables with the 21 centimeter signal. We also then use training sets for the spectral fitting, like what you see here in this cartoon picture. And then finally, we have a Markov chain Monte Carlo algorithm that then allows us to look at the physical parameters. For example, in models of added cooling, we can then constrain the cooling rate as well as the redshift at which that cooling begins. So in things like this, these kind of triangle plots allows us to then constrain with errors on those physical parameters. So that's the direction that we're heading in. We're hoping to be able to launch DAPR in a few years after we complete our instrument maturation project. All right, let me switch gears just a little bit and talk about the next project, sort of the ultimate project that we would like to do from the moon. And that's an array called FARSIDE. And FARSIDE in this case is an acronym like what you see here at the top. We were also funded by NASA this last year to do what they call the probe class study. These are instruments up to $1 billion. And we selected JPL as our partner for this study. My colleague, Greg Hallinan from Caltech, is the deputy PI on this project. And we have just an absolutely outstanding team from JPL working with us on it. You can see here a commercial lander that will bring the array to the surface. And then we have a series of single axle rovers that will deploy a tether and the individual, seen here in red, the individual nodes. They'll be deployed in a spiral-like structure that you see over here that produces good instantaneous UV coverage. So let me tell you a little bit more about what we're going to do with this first array of 128 pairs of cross-dipole antennas. Here, I'm going to switch up gears, talk about the other science case now, which is exoplanets. We're going to draw on first starting in a solar system, why we want to do these radio observations. And it's to recognize what's happened to Mars in that several billion years ago, Mars was wet and warm, as you see in the cartoon picture, but the core of Mars cooled, the magnetic field turned off, and the solar wind then became very effective in stripping the atmosphere and eliminating water from the surface. That we know that stripping has occurred because of the MAVEN satellite, which we built at the University of Colorado, and NASA has flown and continues to be in orbit of Mars today. It has dramatically, this effect has dramatically changed. When the magnetic field shut down, it made Mars into the kind of desert planet that it has today. So when you're looking at habitability of exoplanets, just being in the so-called habitable or water zone is not sufficient. We also have to look at what is the space weather, how active is the star, and the outflow from the star, and does the planet have a magnetic field? Those may be very important ingredients for habitability. Here we can show in this visual, this is a video from my colleague at Caltech. We see two coronal mass ejections hitting two planets. One on the left side is a Mars-like planet. On the right side is an Earth-like planet. And of course, we know in the case of Earth, the magnetic field protects us from the worst effects of these CMEs. And it's also the solar wind illuminates the magnetic field. It produces a auroral kilometric radiation at low frequencies, as well as auroral visible light that is there. So the idea of, can we detect CMEs and planetary magnetic fields in extrasolar planets? The answer is yes. With the right radio telescope, sensitivity, frequency, which drives you to the far side of the moon to be able to do this. The stars that we'll be looking at, the systems we're looking at, are dominated by M dwarfs in our solar neighborhood. We know this from the statistical plot that you see here. There's been surveyed tests. The NASA satellite test is identifying a number of exoplanets. that are located there in the solar neighborhood. Now, the thing about the M-dwarf stars, they're of course smaller and cooler, so the habitable zone around these stars is only about 2/10 of an astronomical unit. So you've got to be a lot closer to the star. But the additional problem you have is these stars also tend to be more active. We know this in visible light in X-rays. And so that could mean that their space weather is more difficult. Here it just shows you some examples. Here's a very bright solar flare that's about 45 times the normal. And here's a flare from an M-dwarf star. Holy cows, 100,000 times. So these stars tend to be more active, which means that it's important to understand their characteristics. So here is a highly stylized cartoon picture of an M-dwarf star with the equivalent of a coronal mass ejection and a type 2 radio burst. Type 2 radio bursts for the sun come from shock waves, which propagate out from the solar corona, re-energize particles, and produce radio emission mostly below 10 megahertz, below the ionospheric cutoff. These large shocks here also light up the magnetic field and enhance radio emission by orders of magnitude. So we have a method of potentially being able to observe. Here you can see actual type 2 radio bursts. This is a white light image on the left-hand side, and then equivalent radio emission from the wind waves. This is frequency versus time on the y-axis, on the x-axis. And once again, you can see that most of the emission is below 10 megahertz in here. But it's a powerful probe, and we can use the analogy to then model what we would expect to see from the exoplanets. The planets themselves, we have to go to low frequencies because the emission is electron cyclotron maser emission, and the frequency is directly proportional to the magnetic field strength. So here, looking at flux density versus frequency, only Jupiter can be seen from the Earth because its magnetic field is strong enough to pop up above the ionospheric cutoff. Everything else, including our own Earth's radio emission, can only be seen from space. In the case of Earth, that emission is below a megahertz or a half a megahertz as well. So once again, we need to go to the surface of the moon to do observations. In fact, for the outer planets in our solar system, as well as exoplanets in other systems. Here's just a table of some of the requirements we came up with from our study. And I just list a few. 128 of these pairs of dipole antennas, 100 meters length at the low frequency. We go down to 100 kilohertz, so 2 orders of magnitude below the ionospheric cutoff is what we're planning to do. That's possible to do these observations, even though most of the galaxy is optically thick. We're only going to be looking at nearby stellar systems out to 10 parsecs or so. And so we can see those against the rest of the background. We're going to be doing all sky imaging, so we'll do roughly 10,000 degrees, or at least the half of the sky we can see from the surface of the moon, 10,000 square degrees. Every minute we will image, and resolution goes from what you see at the low to the high band, from a few degrees to a few arc minutes. And the effective collecting area, because we're dealing with dipole antennas and the beams are large, the collecting area is outrageous here that we get. It's 10 times greater than the SKA, but that's not really fair because it's apples and oranges as far as the frequencies are concerned. But a huge collecting area and sensitivity at the lowest frequency for these kind of observations. Now, where do we go on the moon? So recently, my student Neil Bassett, myself and colleagues, we published a paper, just appeared in Advances in Space Research, in which we did electromagnetic numerical simulations to look at the effects of diffraction around the moon, because these long wavelengths get bent by the edges of the moon. So we studied where Dapper is going to be able to take data above the moon, And so the plot that you're seeing in here is a relative sensitivity. And we need to get down to about 80 dB below the RFI on the near side. And that would give us about 35 minutes of observations above the far side for every 2 hours of the orbit that we'll be making with DAPPER. On the far side for our far side experiment, here we looked at where could we place the array, and we list regions that are quiet, again, below 80 dB at 10 megahertz and at 100 kilohertz. So at the lower frequency, we're much more limited in what we can be able to do here because of the diffraction. For example, the Schrodinger impact basin is not totally radio quiet, and that's where we're going to be going with LuSEE. So that will be an opportunity for us to test, do some ground truth, if you will, of our electromagnetic models. All right, so here's the mission architecture. This is a brand new slide that from work that we presented to JPL management just last week. Shows the basic architecture. Here's our lander, which also has our base station. We will do our communication potentially through NASA's Lunar Gateway that will transmit the data directly back to the Earth. The base station will house our power, also our computer, and we'll use an FX correlator, has been used for ground-based arrays to take the raw data, turn them into visibilities, and the visibilities was what we will transmit back to the Earth. We'll have 4 of these axial rovers that will lay out a tether. The tether will allow us to have power and communications with the base station. And then we found a way to be able to power this by a combination of solar power and batteries, even allowing us to operate as we want to do through the night, because the nighttime is our best observation time. Here's a little bit of a close-up of the lander. We work with the Blue Origin company. This is Jeff Bezos' company. His lander is called the Blue Moon Lander. They've been a partner with us on it. And what you can see on top here are 4 of these axial rovers, which will then be spring-loaded, pop over, like what you see here, and then be lowered to the surface for deployment. This gives you an idea of the size. So we measure these sizes in units of Elon Musk, as you can see here. So we have the rover, when Elon is laying on the lunar surface, is a little shorter than the length of the axial rover. This axial rover has been developed over a period of over 10 years at JPL. And the spool that you're looking at here is where the tether and the electronics will be for the receivers that will be wound around the spool that you're looking at here. A little bit more on that. So the antenna is going to be embedded in the tether. And then we have this very compact electronics. And JPL has also developed some electronics that will survive the night. So they're good for cold weather. So we don't need any added heating. And we think the lunar environment during the day is survivable. So this allows us then to deploy. Each of the 4 arm lengths that we're doing in the spirals that you see here will be a little shy of 12 kilometers. So we'll be deploying 46 kilometers total of tether, as I said, in the spiral-like pattern. And here I mentioned pairs of antennas. So what we do is we deploy them in a zigzag kind of pattern. Here's the overall spiral, and then a blow-up. So we'll put one antenna here that will have a polarization axis like so, and then another one that will be deployed with the axis perpendicular. So this will give us then a sampling of all 4 of the Stokes parameters in these observations. We've also modeled what the UV coverage will look like. And this is actually We place the array onto the lunar surface using a topographic map for the Lunar Reconnaissance Orbiter. Here's the spiral pattern, and we get very good instantaneous UV coverage. You do the Fourier transform. This is the point spread function. It's pretty good. This is basically the equivalent of a dirty map of a point source. And the distribution of RMS and mean look quite good in this case. And this is what the beam widths will look like. Again, we don't need extraordinary resolution for this. We need to be able to differentiate one star system from the next, which we can do with this kind of resolution, because we also don't have, a lot of background. The background has all been eliminated because the galaxy is optically thick. So we're able to differentiate those nearby star systems at the low frequencies. So we're patterning the operations after ground-based telescopes like the Owens Valley LWA that my colleague Greg Hallinan has built and operate, similar to LOFAR in Europe and elsewhere, hundreds of dipole antennas, as you see here in the drone imaging of the LWA. We're going to be, as I mentioned before, we're going to be doing all sky imaging like what the LWA does. This is showing that imaging and identification of radio sources. In our case, we're going to be looking for time variability of the radio sources, because when a CME goes off, it is going to produce type 2 and type 3 radio emission, and also potentially light up the magnetosphere, and the spectrum and the polarization will be different in each case. We expect to generate about 65 gigabytes of data per day, visibilities that we would send back per Earth day, that is, that we would send back to the Earth. Well, when you put all this together, this is basically what we expect to be able to do. So this is a model of the flux density versus distance of these nearby stellar systems. And the different colors represent ranges of models of how the magnetosphere, the radio emission, the auroral radio emission will be enhanced by the stellar wind. And we estimate that we'll be able to see at least several dozen of the nearby planetary magnetospheres of Earth-like planets, including what you've got here is Proxima b, is going to be certainly one that we would want to highlight. Finally, let me just the last thing I want to show is we are also planning on doing a prototype of FARSIDE, which we're now calling PRIME. So it would be a small radio interferometer on the moon. As part of NASA's CLPS program, we're going to be proposing this in the next few months. And here we want to lay down just a few antennas, probably about 6 antennas, either in a spiral or an L-like pattern. Here is what the instantaneous point response function looks like for that array on the surface. We'll use a mini axial rover from a small lander. And what we want to do is, the main reason we want to do this is we'll do some science. We'll look at the sun and Jupiter, but mainly what we want to do is to buy down risk so that we can demonstrate the kind of mobility, deployment, the operations in the thermal environment, and also reflections from the subsystem as well. So that proposal will be going into NASA, as I said, in the next couple months or so. Well, finally, let me just conclude by saying this is a very exciting time. Finally, after decades and decades of thinking about radio astronomy on the moon, now there is real accessibility. NASA, ESA, India, the other countries are all committed to new explorations of the moon with both human as well as unmanned. NASA's commercial lunar payload services is going to be opening up for us, at least in the U.S., for lunar science beginning next year, and then DAPPER and FARSIDE to follow. All of this leading to a what I like to call forward, not back to, but forward to the moon. So with that, I'm going to stop. I'm happy to take some questions at this point.
Thanks, Jack. This is an excellent colloquium. I hope everybody enjoyed. There were almost 67 participants at a time. I was noting down. Thanks, Jack. I mean, this was been really quite an informative and a diverse topic we have covered. And thanks for agreeing to be here. And yeah, we should have you here in person at some point after all this ends. Yeah.
I'd very much like to visit. If we can get out of this COVID situation, that would be a lot of fun, as we've talked about before. But I really enjoyed it today. Thank you for the good attendance. I very much appreciate it.
Thanks a lot. Thanks. Yeah. Bye now.
Bye now.
Thanks everybody for joining. We'll stop here. Thanks.